Hello, my name is Simon. In this tutorial I'll show you how to run and use the particle tracking of orientation and velocity program that we developed. I'll structure this video with first I'll show you a really quick overview of how the algorithm works. That's basically to give you an idea of when I start talking about how to use it, that's going to be necessary. I really recommend you go read the report on it, but here's a quick walkthrough. Afterwards I'll show you how to set up and run a test case. I'll be assuming you've already installed the program successfully. That can be done by reading the instructions on GitLab, or I also added a YouTube tutorial where I go through it. I'll also be assuming you know how to calibrate and configure your calibration to work within this framework. If you haven't managed that yet, there's also a YouTube tutorial for doing that. Now I will go over how the program works and what we're trying to accomplish with it, essentially. So I prepared this super short presentation. So what we're trying to do here is basically measure non-spherical particles. Now this could be a cube or some of these very weird irregular shapes. In our case, we're measuring using a settling experiment. So we have a tall water tank, and then we're putting the particles underwater, and then they flow downwards. In this example, we have 4 cameras, but you can just assume that we have one here, camera 1 and camera 2, and the others are not used. And then as the particle passes through, we want to measure how it moves. And then in the end, the output will be something like this, right? So this is how the cube has fallen through our measurement domain. What we see is we get both the position and the orientation of all of these shapes. And we see that there are some, if I go to the next, I'll see 13 particles here, see that they spiral and they do all kinds of funny things. And this is basically what we want to measure. So how do we do this? And that's basically what's important for you to understand is we have this setup, and now just assume we have camera 1 and 2 here. So they film the particle against this strong backlight, and then after background subtraction we get an image like this, one for camera 1, one for camera 2. These we call the target images. Now the whole game of the algorithm is to create synthetic images that match up with the target image. So when we have we assume we know the shape of the particle we're trying to track, and then we can move this and rotate it in 3-dimensional space on the computer. Then we can project it to each camera using our camera calibration. That's where this is important. Then we can rasterize it, creating what we call a synthetic image. And then we take this synthetic image and we try to match this to our target image here. And this is done in an optimization loop, which is illustrated below here. So basically we start at time step whatever, of course, where we recorded our cameras, and then we load the target images, which we denote IT, these two, right? Then we start optimization. So then the optimizer suggests some position and some rotation of the synthetic particle. Then we create the synthetic images, these over here, and then we compare the target images with the synthetic images, creating these residual images, which we evaluate into a cost. And if we think this cost is low enough, then we say, well, this position and orientation here must be added to this time step, and then we move on to the next. If we haven't converged, then we say, okay, optimizer, give me a better guess. That means we iterate through this some number of times before we get an acceptable answer. Okay, right. So what it's about is we're trying to run an optimization comparing the target images to these synthetically generated images. Next, I'll show you how to run the program. First, I'll close down this presentation, and then you'll see I have a terminal open here, and then where I downloaded the program here. So first I open up this folder, put this over here. Then if I go under tutorials and tutorial synthetic data, then this is what I'll be going through how to run today. You'll notice there are a few things in here. So first, the calibration parameters. These are the output from our calibration. If you need help doing this, see that tutorial. Then for camera 1, the images captured on camera 1 of the particle moving. Similarly for camera 2, or of course here I have 0 indexed them, but the principle is the same. These images of course needs to be synced by number. And then I have tracks where the data will be output. I'll come back to this opt images. If I open up the configure file, this is the most important file for the user. This sets all settings about how the program is run. So under path here, you specify the path. That's basically where the program should look for the calibration or the images, or where it should look for the shape files, and where it should output the tracks. The settings are a bunch of settings of how the program will run, which you don't need to understand all of these. I'll go through the most important in this video. To set this up, I'll just go through them one by one. Let's start with the path. Calibration should point to where our calibration is. So I go under calibration parameters and I just copy this path in here. If you save the files like this, the program will know how to read it. Then I need to set images. That's where it loads the images. So I set for camera 0, it's this folder. The name of the files here is not important. It just needs to end with a number. And that number needs to be synced across camera 0 in this case and camera 1. And if you have more, then for all of the cameras. Like this. Background images. If we want to background subtract our images before they're put into the program, then we put in the path to where we can find background images here. One common method is simply put the same path as where we saved all the images. And then if we take a bunch of, and then set this background images span to, for example, 0 to 100, then it will read the first 100 images in this path and use those, the average of that, as the background image. Oftentimes when we run an experiment, right, we start filming and then a few seconds pass before the particles start to enter our domain. Then this approach will putting these paths in here will make sense. In this case, the background subtraction has already been done. So we write null here. Next we need to specify where the shapes are saved, so where these .stl files. For this tutorial I provided you in the PTOV library under shapes. I provided you with the shapes. Here are more shapes than comes with the library. The important one in this example is palm pellet 01 STL, which is in your folder. So I just specify the path to where it should look for these. Then I need to specify tracks. So I go back under tutorials, tutorial synthetic data, and then conveniently I have this called tracks. It will overwrite whatever is in here. Keep note of that. The next thing is we want to specify the images for the file paths. This opt images file path. That's when it runs, when it optimizes in this loop I showed you before, then it comes out with a, when it finds its optimal orientation and position, then it will save the target image, the synthetic image, and the residual image, which we can then look at later, which is convenient for debugging. If you put no path in here, it won't save it. But in this case, I use this folder and I specify this path. Great. I will now run the program as is, and then afterwards I'll go through these settings. To run the program, I'll go through my IDE, but of course you don't have to do that. So first I'll activate the environment we created in the installation tutorial, and I'll open up Spider. You can use whatever IDE, of course, or run it straight off the terminal. That doesn't really matter. It automatically opens the run main file for me, but of course that may not happen to you, so I'll just close this, and then I will go to where I saved the PTOV library, so from, in my case, desktop and PTOV, and then this file runmain.py, and it'll look like this. The only thing we have to do here is specify where it looks for the config.json file we saw earlier, this config.json file. You'll notice this is a list in case you want multiple jobs to be run in succession. But in my case, we just want to specify the path to this PTOV tutorials synthetic data. Put this in here, and then of course config.json is whatever the file is here. We can now press run. I have this set up in the debugging settings, you could say, for this config. I'll go over how to change that afterwards. So when we run here, it first runs a particle tracking algorithm on the contour centers, which is what we see here. That's done quickly, and now the optimization starts. So now it's changing the synthetic image, trying to match it to this target image. Here we see the residual between the two. Try it a few times, then it finds a good orientation, and then it optimizes that again. So there's a coarse pass here, it likes this orientation, and then it optimizes until we get a really nice match. And this basically repeats until, and this is the image at the end of the optimization that's saved in this opt images, this exact plot you see here. That's nice, because then we can see if something has gone wrong. Of course, this is running really slowly because it needs to draw this image lots of times. So now I'll show you how to change that. And I'll also talk about what the other settings in the config file do. So if you notice here, We iterate for some amount of time, and then there's a cost on the y-axis. I'll come back to this, so just keep that in mind. So now I'll just shut down the run. Now we go to the config file, and I'll just open this. First I'll actually go here to where we ran our job. I'll go under opt images, and we'll see it saved this image here we saw from before a couple of times. Let me just put that here, because that'll be useful for when I need to explain these settings. Okay, so let's go through these things, the most important parameters, one by one. So background images span, we already explained this. Use only n images. This is basically when we have all of these images for each camera. If I only wanted to use images 0 to 10, then I specify it like this. In my case, I write null, then it takes all the images that are in these folders. Show images. This should be 0 or 1. If it's 1, then it opens the windows where we can see what's going on. If it's 0, it doesn't. Code runs a lot faster if you have this at 0, so if you batch this while you're not looking at your computer, then you should put it to 0. But for debugging, if something goes wrong or we need to set some settings, it's nice to set this to 1. This number, the first settings here are related to the PTV, so where we track just the center of the contours and don't try to find orientation. This is the maximum epipolar line distance in pixels that we can choose. We set this to 40, which is a huge number if you think about it, but the idea is if particles are occluding on one camera but not on another, then we can still get a very inaccurate but an estimated position for these. And that means that once we get to the optimization phase, then we have a good, at least a decent starting point, and then the error in the position will be fixed during the optimization. The nearest neighbor PTV maximum distance is between each frames when we do PTV, so only tracking the center of the contours. How far do we expect at most the particles to move within a frame? And this is in millimeters. The stuff saved down here is related to the orientation. So first, find orientation. If it's 0, we don't find orientation. If it's 1, we find orientation. The next important parameter is this model particle reduction. So basically we have the mesh of the particle. So if we set this to 0.75, that means it reduces, the code reduces the number of phases using a PyVista algorithm by 75%. The next important parameter is this perturb maximum cost limit. So if we look here, the first time we observed on the 0th time step, we restart the optimization multiple times, right? We run for 25 iterations, then we restart. Do this a couple times until we get something we like, and then we do the long find pass. The number we set here is once the course pass reaches less than 2e minus 2, which of course we see happens here, then it goes to find pass. So if we find that it restarts too many times, and we can increase it. If it converges to a wrong minima, we should decrease this. The next important parameter is the maximum number of restarts, which is what this is. So each time we restart here, then a counter ticks up, and once it reaches 50, then it says, okay, we must have found the best possible orientation. Draw image every is if we have show images on, how many iterations should pass between us drawing this image. I have this at 1, which is why it runs really slowly. Finally, these is related to the shape. So this algorithm needs the shape of the particle in order to generate this synthetic image. So we specify all the names in this path. If you remember up here, we specified a path to where the shapes are located. Then we specify the names of the STL files observed. So these may be called shape2.stl and so on. We can go on, right? In this case, we have only one, so it's like this. Now, in the case where we have 2 particles present in our domain, then there are 2 options. Either shape names in orders is equal 1 or 0. If it's 1, then it assumes that the first particle to enter the measuring volume is this, followed by this, followed by the next, and so on. This makes it computationally a lot easier, because if this is set to 0, then we assume that the algorithm doesn't know if this is the first particle to enter the measurement volume or if it's this one. So it tries to figure this out basically by doing the exact same optimization you see over here. In this case, we have only 1 particle, so we might as well set this to 1. Okay, so This should hopefully teach you how to use the config.json file. If you have any questions, then you can send an email at the specified email on the library. Just to show a full run, then I will now set the show images to 0 to speed up the code significantly, and then I'll rerun the whole code using this setup. So I close this down and I run the code again. I'll speed this up. So what will have been populated now is this tracks here. We'll have a tracks01.json, and this is basically, I mean, if you had more than one particle, you had more files here. This contains the time step it was observed, the position at each time step, the position the optimizer found. So the position here is the PTOV position. Then you have the optimized position here. Then you have the cost of the optimization problem. You see actually that probably we should have optimized a bit more in the first iteration, as the rest have very uniform size. Then you have the orientation vector as an axis angle here for every time step. And if we scroll down to the bottom, some more information. For example, what is the shape name of the particle? So it was this palm pellet 01 that we used here, and the length. This .json format can be easily read using the track class described here. If we open this up, there's something called load from JSON. So I recommend using this, and it'll basically give you the track as an object that is easy to use. That's also what gets spit out of the program here. So if I run tracks from before, 0, because I only have one, and pos, then this is the positions. Or ori, and we have the orientations. And then it's the exact same thing you get out of running this load from JSON. So that's the contents of the track file. The other stuff that we get is under, if we go back under tutorial synthetic data, it's these opt images, which is saved for each time step, right? So if we go through these, then we see that we get a nice match between the target images on the left, the synthetic images here, and that the residual image is very small here. And we can scroll through all the images and see this looks really nice. Great, you've now run your first case, so it's up to you now. Thank you for watching.